Hi, welcome to Algebra 2 Common Core. Today we're going to look at quadratic linear systems of equations. So starting with the first exercise, we want to algebraically find the intersection of x squared plus y squared equals 17 and y equals x minus 3. After we find those intersections, we will then draw a sketch of the system. So when I look at my first equation, I notice that since it's in the form of x squared plus y squared equals 17, that should look familiar from my last lesson. I see that that's going to be the equation of a circle. And when I look at the second equation, y equals x minus 3, that's linear in form because it's in the form of y equals mx plus b. So to solve algebraically, I'm going to use the method of substitution. So for the method of substitution, I want to start with the easier equation, the linear one, and be sure that it's in y equals mx plus b form. Since it is, I'm going to then take my value for y and substitute it into the other equation where I see a y. So this equation is going to become x squared plus the quantity x minus 3 squared equals 17. So I'm replacing the y in the circle equation with what y is equal to according to the linear equation. So our goal was to have an equation in terms of one variable that I'll then be able to solve. Let's simplify this equation. So I'm going to multiply out the x minus 3 squared. If you have to, write down x minus 3 times itself and go ahead and do that multiplication. So I have x squared plus x times x is x squared. Outers give me negative 3x, inners negative 3x, so that's going to combine to give me a negative 6x. Negative 3 times negative 3, positive 9. Equals 17. I notice that this is a quadratic equation, so I want to put this in standard form. So I'm going to say 2x squared, combining my x squared terms, minus 6x, and then let's subtract 17 from both sides of the equation, so I'll have minus 8 equals 0. Now this is quadratic, but I see that it has a GCF, so I'm going to factor out my 2. And what's left over is the trinomial x squared minus 3x minus 4. We know how to factor this, so we're going to say 2 times x minus 4 times x plus 1 equals 0. Now let's go ahead and make our t-bar. Of course, when I've got a constant in front, I don't need to set that equal to 0 because 2 doesn't equal 0. So instead, let's look at the other two factors. When x minus 4 is equal to 0, I know that x is equal to 4. And if x plus 1 is equal to 0, that gives me the solution x is equal to negative 1. Now I'm not done because I know that I've got a circle and a line and I want to know where they intersect, so that means that I need to find a point of intersection. So of course my last step is to solve for y for each of these ordered pairs. So going back to my y equation, y is equal to x minus 3. So if I put 4 in for x, substituting, I get y is equal to 1. So therefore, one point of intersection will be the point 4, 1. Let's do the same thing with x equals negative 1. So if y is equal to x minus 3, that tells me that in this case, y is equal to negative 1 minus 3, which is negative 4. So my ordered pair, negative 1, negative 4. So I see that I have 2 points of intersection here, 2 places where the circle is going to cross with the line. Now let's go ahead and sketch a graph of this. I'm going to start with the circle, and I see that the equation is x squared plus y squared equals 17. So because it's got x squared plus y squared, that tells me that the center of the circle is going to be the origin. 17 is not a perfect square, but it's just a little bit bigger than 16, so that tells me that the radius is going to be just a tiny bit bigger than 4. So from the center, I'm going to count 4 to the right and make a point on my circle, 4 up and go a little bit further than 4 and make a point on the circle, 4 to the left and go a tiny bit further and make another point on the circle, and the same with going 4 down and a little bit more. So I am getting this circle, looks something like that, x squared plus y squared equals 17. Now we want to graph the line as well, and that's just in y equals mx plus b form. So I'm going to start with my intercept of -3, and let's do a slope of up 1 over 1, up 1 over 1 to get points on my line. I could also go the other direction, down 1 to the left, and I see that I have this line. Now we of course want to label our line with y equals x minus 3, label our circle with x squared plus y squared equals 17, and of course label our points of intersection. We found them algebraically. Here's 1, 4, 1, and -1, -4. But we also see that those answers make sense according to my graph. Let's try exercise 2 algebraically as well. So I'm trying to find the intersection of y equals 2x squared minus x minus 5 and 5x minus y equals -3. So if I look carefully at the first equation, I should recognize that this is the equation of a parabola. And then my second equation, because it's got x to the first and y to the first, that's a linear equation, but let's get it into y equals mx plus b form. So I'm probably going to subtract 5x from both sides of the equation. So that gives me -y is equal to -5x minus 3. And then divide both sides by -1, so y is equal to 5x plus 3. So let's solve algebraically first. We're going to do the same thing that we did on the last example, and let's replace the y in the parabola equation with what it's equal to from the line. So 5x plus 3 is equal to 2x squared minus x minus 5. So we can solve this quadratic equation by putting it in standard form. So let's subtract 5x from both sides. Let's subtract 3. And I now have 2x squared minus 6x minus 8 equals 0. This looks really familiar. I think it's the same quadratic we had on the last example. So factoring out a 2, I now have x squared minus 3x minus 4. And yes, this is factorable. So 2 times x minus 4 times x plus 1 equals 0. Solving for my x values, I get x minus 4 is equal to 0, so x must be 4. X plus 1 is equal to 0, so x must be equal to -1. And just like the last example, we need to find the y value by going back to our linear equation. You could actually go back to either equation, but the linear one is easier. So 5 times 4 plus 3, that's 23. And then in my second equation, 5 times -1 plus 3, that's giving me -2. So my 2 points of intersection should be 4, 23, and -1, -2. Now I'd like you to go ahead and find your graphing calculator and use it to create a table of values for the parabola. Graph what you can. I know this is a little bit limited of an axis, coordinate axis here because the numbers don't go that big, but graph what you can, and also graph the line and see if it matches up with these ordered pairs. Let's take a look at the graphs I've got the parabola, and notice how I've labeled it y equals 2x squared minus x minus 5. And I've got the linear function, y equals 5x plus 3. So that was nice and easy to graph. I used a table of values for the parabola, and I used the slope-intercept form for the line. Now, because my second point of intersection has such a big y value, I'm not able to see it on this graph, but of course I could go to my graphing calculator and adjust the y max on my calculator so that I would be able to see that point of intersection and verify that they do cross there. Now, speaking of our calculator, let's use our graphing calculator to work on exercise number 3. So for this problem, it says, which of the following systems of equations has exactly one point of intersection? Now, I think rather than trying to solve each of these algebraically to find the points of intersection, I would like to take a look at my graphing calculator. And on my calculator, I can either use the graph to find the points of intersection, or I can look at the table and see where the points of intersection are. So for example, with choice number 1, I'm going to enter in y1 x squared minus 5x plus 7. And in y2, let's rewrite this equation. So I'm going to have it in y equals mx plus b form, so it's going to be y equals 2x plus 1. And then I think I'll go to my table and see how many points of intersection I have, or again, I could look on the graph as well. What I'd like you to do for each of these 4, don't stop even if you find the answer, but I want you to do this for all 4 of them. I want you to find how many points of intersection there are in the system, and then find those points of intersection. Once you have all 4 of them, then come on back and we'll talk about which one we're going to choose as our final answer. So compare your points of intersection with the ones that I found for each of the selections. So in number 1, I found 2 points of intersection, one at 1,3 and one at 6,13. For number 2, I did find 1 point of intersection at negative 1,3. Hopefully you noticed that that line, being a horizontal line, turned out to be tangent to the parabola at the vertex. Number 3, I got 2 points of intersection, 1, 2 and negative 2, 11. And number 4, the parabola and the line did not intersect at all, so there were 0 points of intersection. So we were looking for which system had exactly 1 point of intersection, so I'm going to pick choice number 2. Now what I'd like you to do is please do the you try it. So solve the system algebraically, and then come back and check your work and your answers with the solutions that I have. Please compare your algebraic work with mine. I substituted x plus 1 for the y in the circle equation. Then I multiplied x plus 1 times x plus 1 and put the quadratic equation in standard form. I could see a GCF, so I factored out a 2, and I was left with the quadratic x squared plus x minus 12. That's a nice easy trinomial to factor as x plus 4 times x minus 3. Setting each factor equal to 0, I have 2 solutions for x, negative 4 and positive 3. I like to go back to the linear equation to find the y that goes with each one. So for the first one, I get the point of intersection negative 4, negative 3. And for the second one, I get the point of intersection 3, 4. Now you always know to check these by substituting back into either original equation, and in fact both original equations would work. So plugging either point back into the line or the circle should give me a true equation. We'll do lots more work in class on solving systems both algebraically and graphically. Thanks for working with me tonight, and have a great night.